45 minutes or Let's go ahead and get started. Okay, so first of all, welcome to the first AHU SDSCI Joint Colloquium Talk of the Year. My name is Cameron Trapp. I'm a postdoc here working in the Foggy collaboration. And before that, I worked on the fire simulations, which is why I'm very excited to be introducing our speaker today, Phil Hopkins. So just a little bit about Phil. He received his bachelor's at Princeton University before going on and doing his master's and PhD at Harvard. Following this, Phil was a Miller and Einstein postdoctoral fellow at UC Berkeley before his current position as professor of theoretical astrophysics at Caltech, where he is the PI of the fire collaboration as well as pursuing a lot of other theoretical pursuits. So yeah, today's Phil is going to be talking about what I think is one of the coolest modern computational astrophysics projects, which is linking two very different scales and simulations. So take it away, Phil.
Thank you very much, Cameron. Thank you, everybody, for having me out. It's been a busy but great day, a lot of great conversations. There's so many people here to talk to. I really have to come back for another visit because I could only spend 2 days, and there's like, I literally see like 10 people in the audience that I want to talk to who I know aren't on my schedule. So hopefully I'll be able to talk to many of you more soon. And there's many things to talk about. I'm going to talk about, as Cameron said, this recent project linking disparate scales that we've been working on from the theory and numerical modeling side for a long time, particularly particularly in the context of black holes, although I'll mention a couple other applications that we're working on very briefly. And this is work with a lot of students, and I'm going to single out a little more as we go. But to set things up and to give a little context of where these scales connect and come from, but also to explain, I titled this Forged in Fire. Where does that name come from? Well, it's the combination of two projects working from sort of large scales down and small scales up. One of which is our large multi-institution FIRE collaboration that Cameron mentioned. So this is a project trying to understand galaxy formation, and there's a lot of exciting recent work that I won't have any time to talk about on modeling JWST galaxies, disks settling in the formation of galactic disks, how feedback from galaxies interacts with the CGM and IGM. I just wanted to single out a few of the great junior scientists who are working on projects with us. But this has been a project oriented at trying to add more multiphysics from sort of the top scales down, beginning from cosmological simulations, zooming in on galaxy formation. But of course, these are strongly coupled to very small scales. If you want to follow how supernovae influence a galaxy, you, on large scales, need to know something like the effective momentum and energy and metal and mass deposition of supernovae, which means evolving them through the Sedov-Taylor phases and cooling phases and interacting blast waves from multiple supernovae forming superbubbles. And so on smaller scales, we've had a separate project started by a couple of former graduate students, Mike Grudich and David Gusenyov. Nadine Solomon is a student who just graduated who's been doing a lot of recent work in StarForge. And this is a project to try and simulate and model the sort of very small scales of star formation, looking at individual molecular clouds where you have more like 100,000 cells per star, so that you're actually resolving and predicting the masses of individual stars in the simulation. And this movie was showing a little cloud where it starts forming some massive stars, and you see things like protostellar jets that launch out from those stars, as well as towards a little more evolution, you start seeing expanding H2 regions and cavities that disrupt this. And you can start making predictions for things like the stellar initial mass function, the formation of bound stellar clusters, stellar multiplicity, formation of very massive stars in very special environments, and the microphysics of the ISM, things like thermochemistry and observables on very small scales compared to these galactic scales. But the project that we've been building towards, called Forged in Fire, is essentially stitching all of this together. And we've been, for many years, very carefully building both of these frameworks so that all of the physics that isn't locked to a scale, for example, what do I mean locked to a scale? Something like the model, each star particle here represents a star and follows an individual stellar evolution track. Representative of a true star as it accretes, as it evolves. Whereas here, typically in a galaxy simulation, you don't resolve individual stars. So a star particle really represents a stellar population, an ensemble of many stars, and you assume a mass function of those stars, et cetera. But there's no reason that, say, the treatment of magnetic fields and hydrodynamics in this simulation needs to be different from this simulation. And it's not. We've built it very carefully so that even though some things, maybe you can make different approximations for cooling in this simulation and this simulation, but you don't have to. You can write one set of cooling functions that can do both simulations. And so we've built it so that we can ultimately run all of this in the same simulation, where the only difference is basically depending on your resolution, whether you assume you're forming a group of stars or a single star at a time. And that's what this project is designed about, is being able to simulate these large dynamic ranges of scales at once, not just from a resolution point of view, but from a physics point of view. And that's really important, and I'll come back to it. A few examples where we've been looking at applying this, and I'll just advertise very briefly, are things like, I'll make a mention of applications for dust and planet formation and ISM substructure. I'll also, at the very end of the talk, mention very briefly some work we've been doing with cosmic rays and other astrophysical plasma physics. Something I won't mention at all, but a couple former student Jacob Shen and current student Isabel Sands have been looking at how we can use these models to better probe astrophysical tests of different particle dark matter models. And of course, there's been a lot of fun numerical methods that have come out of this, of new ways to develop extreme dynamic range simulations, multi-fluid simulations, a lot of fun numerical stuff. And again, these are just advertisements for some of the great work by different students and postdocs on this. So just to give one example that's not the black hole stuff that I'm going to spend the rest of the talk about is one example of these very small scales coupling to very large is dust in the ISM. And we all know dust is important, and we all know dust has a lot of messy microphysics. But one of the pieces of microphysics that we often neglect while we argue about dust chemistry is dust dynamics. Dust has an incredibly rich dynamics in the interstellar medium. Dust does not just glue itself to gas and move with the gas. It moves as a complicated group of aerodynamic particles that have different aerodynamic properties depending on the composition and size of the dust grains through gas if it's being irradiated or having any other differential forces on the dust and gas. And then it has aerodynamic drag and things like that. And dust is also charged, so it interacts with the magnetic fields. And when you actually look at this in detail and, for example, try and simulate it, this point of a star radiating a batch of dust that moves through some gas, if you simulate this in a little box, what you see is that there's an enormous family of instabilities that occur. Whenever you try and push particulates through another fluid, you can show, with Jono square, we show there's actually an infinitely large superfamily of instabilities. And the only one that, to our knowledge, has been studied in astrophysics is the streaming instability of grains in circumstellar disks, which is a big part of the planet formation story these days for all of you who work in that field. That one was discovered before this, but it's the only one that had been studied in the astrophysical context. But this actually happens everywhere that there's dust. The only question is, what's the size scale and the growth time scale of the instabilities for what they would do? And sometimes they're going to happen on microscales, but they could still nonlinearly influence things like the effective optical depth of the medium or the dust coagulation and growth and shattering. Sometimes they can happen on macro scales. And so with Nadine Sullivan and Eric Mosley, who also implemented a lot of these simulations and did the real numerical work, we showed that these could reproduce a lot of dust structures we see in things like nearby molecular clouds and H2 regions, and give you all sorts of unique types of variability. Nadine also showed, she wrote a whole bunch of papers, and I'm just advertising a few of them here. I won't mention all of these because there's not enough time. She showed they can give you unique forms of variability of dust to gas ratio fluctuations along the line of sight for things like AGN winds out of the dusty torus, as well as things like R-core Bohr and AGB winds, that this can affect metal abundance patterns of stars. These small scale fluctuations in the dust abundances will get imprinted in the abundances of stars that form out of that medium. And in fact, can actually trick you sometimes, because you can form stars that have a small excess abundance of refractory elements in their surface because they accreted a little more dust. And what does that look exactly like? Observation, it looks exactly like a star that ate an Earth-like or, you know, a planet, because a planet's just a bunch of dust grains glued together, basically, if we're zooming back out. Another really fun thing Nadine proposed towards the end of her PhD is that these also provide a new type of cosmic battery mechanism, a way to generate magnetic fields in the early universe. The idea is that you have something like stellar radiation after, say, your first stars form and deposit some metals in some dust grains. They push the dust through the gas, but the dust is almost always charged. And in fact, in mostly neutral environments is where this is most effective, because the dust soaks up that free electrostatic charge really easily, just like dust bunnies in your house want to. And then these instabilities generate a curl in the motion of the dust, which generates a magnetic field. And you can spontaneously generate quite strong magnetic fields in very dense gas near stars with this mechanism on very short time scales. And this is interesting because the other kinds of battery mechanisms, for people who think about where cosmic magnetic fields come from, the other classical batteries that the plasma physicists like to think about tend to work best in the exact opposite parameter space. They tend to work best when the plasmas are extremely hot and very tenuous and very weakly collisional, which is the exact opposite regime of this. So it's not that those can't happen, it's just that they'll happen in very different environments. So there's a lot of fun things to explore. And now what we're trying to do is use new numerical methods to try and embed this in larger scale simulations to see how far up can the amplification of these small scale fields go to connect to like a turbulent dynamo on larger scales by doing things like hierarchical zooming in and zooming out of patches of a turbulent medium with dust dynamics and things like that. But that's all I'm going to say about all this fun dust and ISM stuff. And now let's talk about another example where these very small scales couple to very large, which is black holes. And this will be the rest of the talk. So we know supermassive black holes exist at the centers of many galaxies, famously, and we know that they're extremely multi-scale. So you've got your event horizon, which for a typical supermassive black hole has a scale of order in AU, depends on the mass, obviously. And we know that effects of the black holes can propagate out to at least of order a megaparsec or hundreds of kiloparsec scales. We see it very directly in famous radio jets and other examples. And this scale dynamic range is tremendously difficult to model because the energy here we know is enough to in principle change the dynamics of the medium on large scales, but it's coming from these microscales. So we need to understand how this creates this jet. But then we also need to understand how this feedback from the AGN regulates the accretion that ultimately comes into here. So this is a coupled problem, and that's what makes this fundamentally challenging. If this were a pure top-down or bottom-up problem, if the coupling only worked in one causal direction, this would be a relatively straightforward problem to solve, but it's not a one-directional problem. It's a bidirectional problem, and that's what the small and large scales are coupled, and that's what makes it hard. So again, it's multi-scale, as I just mentioned. But the other thing that makes covering this range of scales hard, and this comes back to this forged in fire argument, is that there's a lot of different physics that are happening that can be important to this problem. And in particular, there's different physics that might be more or less important on different scales. So there's a lot of things that we neglect in galaxy formation simulations that you can't neglect if you're simulating an accretion disk, and vice versa. Right? Nobody's modeling the inner 100 RG around a black hole and worrying about star formation. Well, I shouldn't say nobody, but generally we make a lot of approximations on either side, and we want to stitch these together. So as a result, partly of this and partly of a lot of observational challenges, I'd say these three sort of zeroth order questions about supermassive black holes still remain very much open. Now, where do they come from? What are the seeds of these things? How do they grow? And what do they do to their surroundings? And these are very much still the big questions in the field. So I'm going to talk a little about each of these questions. I'm going to go relatively briefly through the first one because it's the fact that it's the one that I think we know least about, both observationally and theoretically. But I'll still mention a few things we've been doing to try and understand this problem. And for each of these, I'm going to say a couple pieces of conventional wisdom that I think are wrong in the field. Now, I'm oversimplifying, yes, and you can argue that maybe these conventional wisdom things aren't really conventional wisdom, and I'm putting a little bit of a straw man, and yes, but I'm going to do it anyways because I think pedagogically it works well. So one common argument you see a lot, especially recently with JWST observations, is that the existence of very massive black holes in the early universe requires some exotic mechanism like direct collapse, skip the whole small black hole stage and go directly to supermassive or nearly supermassive black hole. Another common assumption that's built into many models is that black holes form somewhere and then they very efficiently sink to galaxy centers via processes like dynamical friction, where they can then grow and get gas funneled down onto them. Now, on the growth side, the problem, just to introduce those of you who aren't familiar with this, the problem with high mass black holes in the early universe is the time required to grow them. So if you assume that black holes grow at some fixed multiple of the Eddington limit, and that the radiative efficiency, the fraction of m dot c squared that you convert to light of the black hole is constant, that's this lambda Eddington, then the black hole will grow exponentially with an e-folding time, if this is 1, of about 50 million years. And the problem is, if you start from a very small seed, you can't get enough e-folds in time to build up to, say, 10 to the 9 solar masses in the very early universe. And this problem's been around for a long time. And there's two basic ways around this in this simple expression. One is you can increase m initial, which is basically the heavy seed or direct collapse type idea, or you can increase lambda Eddington, allow super Eddington accretion. Super Eddington here doesn't necessarily mean exceed the Eddington limit in light, which is what the Eddington limit is properly defined by. It means super Eddington accretion rate, which is itself a bit of a weird concept, but that's how we tend to talk about it. Now, and the point is, yes, this is just the time scale problem. So the problem I have, just as a pure theoretical bias, I have more than one, but one of my issues with these heavy seed models is they don't actually help you that much, because this is an exponential. So if I want to know delta t, I take the log of both sides, so I only gain logarithmically by making this bigger, right? So if I'm Eddington limited and I want to grow from 100 solar masses to 10 to the 9, it takes me 800 million years. That's a really long time in the early universe. I have to be on all the time for 800 million years. Let's say I jump all the way to 100,000 solar masses, get a really huge direct collapse black hole. Well, now it takes me 500 million years. That's the same. So I haven't gained that much. On the other hand, if I have a brief episode where I go to a few hundred times the Eddington limit, then I can do this in order a million years for either model. So there's a good reason why a lot of people have thought about this, and there's a lot of arguments from the accretion disk community that it's not impossible to go to order 100 times the Eddington accretion limit, at least under the right circumstances, if you can fuel enough into the accretion disk. And there's still open questions there to be worked out. We've been thinking about this from somewhat larger radii. Can a black hole sustain capture of gas from its environment on these hyper-Eddington accretion to potentially fuel hyper-Eddington accretion at a fast enough rate for a long enough time? And this, there's a series of papers led by a former student, Yanlong Shi, and Kyle Kremer that showed that there's actually quite a surprisingly wide amount of parameter space that seems fairly reasonable where this can happen in very dense massive sort of clouds that form very dense, massive bound star clusters, but are not in any way beyond what we see as the most extreme, massive, dense bound star clusters. And this wouldn't happen in every typical globular. This is more like the really extreme ones here. You could also do this with even more extreme seeds. With Jacob Shen, we worked on exotic self-interacting dark matter models that allow you to collapse straight to 10 to the 8 solar masses. If you let me break the standard model, I can give you lots of ways to make these things. And I think some of these are fun ideas that are worth investigating. I was actually sure this, I had Jacob start working on this because I was sure that this model, if it was tuned to make these black holes, would eat everything and we'd be able to rule it out definitively. But it turns out there's some reasons why it doesn't run away completely, which is kind of interesting. But my money's here if it's not obvious. But there's also a lot of problems with this idea of even if you can, in principle, fuel these, one of the problems growing these things rapidly that has emerged is that actually getting them to efficiently sync to galaxy centers, or even to define a galaxy center for them to sync to and have coherent angular momentum transfer onto them, is quite challenging. So here's some simulations that form some nice, beautiful disk galaxies at redshift 0. But you saw in that simulation, this is just the gas at high redshifts. It's a bursty, clumpy mess. And we see a lot of, clumpy messes at high Z. And this galaxy is some dwarf thing that's, blowing up a lot of its gas from cycles of star formation and feedback. That can tend to produce a lot of, episodes of things blowing out. That tends to give you a lot of stars that are in a bulge or a thick disk or an extended halo, but not a very thin disk. And it's not till later times that it sort of calms down. And there's a huge amount of interesting stuff happening with Gaia and other constraints to try and understand this transition of galaxies from sort of thick to thin over cosmic time. I could give a whole colloquium about this, but I don't have the time. And also, I will just mention, this has also been linked potentially to a lot of other JWST observations, perhaps explaining the excess of very UV bright galaxies. If you have these bursts, it allows you to, for a relatively small cost in stellar mass, so you don't break anything at later redshifts, create a lot of UV bright systems and reconcile the UV luminosity function. So there's good reason to believe, and these are just a couple of them, that this is probably happening to some extent in nature, but it does make the black hole growth problem a lot harder. And on top of that, Linhao Ma, another recent former student, looked at the actual detailed dynamics of this and showed that when you have these clumpy, bursty galaxies, the dynamical friction process just doesn't work, which makes sense if you think about it for a minute. It's assuming a sort of perfectly well-defined smooth potential with a well-defined central point, slowly decaying circular orbits with an effectively infinite homogeneous background medium is how we derive those scalings. And people have derived it from messier cases. But if your medium is sufficiently clumpy, there isn't even a center to point to, and your black hole just ping-pongs around. Also, if your black hole is not supermassive, it's not more massive than the random star clusters. So why would it sync compared to them? It's just another test particle in the system, basically. So one thing that we've been working on is how do you get around all of these? Well, it probably has a lot to do with environments, and it may be connected to little red dots, or maybe I'm just obligated to say the word little red dot when I talk about AGN. But Yanlong Shi, again, worked on this and has a couple other papers in prep, looking at what are the conditions where you can sort of attempt to solve all of these problems at once. And you really need a sort of dense cradle of formation, which I already alluded to, dense regions. So if you take an initial gas complex that's low density, by which I mean something more like a molecular cloud we see today in the Milky Way, what tends to happen is you turn a couple % of its mass into stars, it blows itself up. If there's any black holes there, they accrete almost negligibly before this episode is done. On the other hand, if you have a dense enough complex, it's been known for a long time in the star formation community that above a sort of critical gravitational force density or mass per unit area, you'll have sort of runaway collapse where stellar feedback is unable to efficiently blow up the cloud. You'll form a dense bound star cluster. And if that's massive enough, what you get is these star clusters form hierarchically. They form dense subclusters that assemble extremely quickly. And those subclusters, if there's any free-floating 10, 100 solar mass black hole around, they grab it. It can sink very quickly to the center of its small subcluster, and then the subcluster carries it, just like a galaxy would carry a black hole via dynamical friction at low redshift in a galaxy-galaxy merger, into the very center of the subcluster. The stars around it provide an anchoring potential to fuel a lot of gas in, and you get a phase of highly hyper-Eddington accretion, which also happens to have, I'll come back to this, these strongly magnetized accretion disks in these simulations. And this ends up looking a lot in size, in luminosity, in the sort of gas densities at the radii we can resolve, which aren't quite the radii we really want to resolve. We're zooming in right now with these forged and fire methods on this. Literally, it's running as I speak. It has a lot of the properties that during this phase look a lot like a little red dot, and we kind of kicked ourselves when Yanlong was finally writing this paper up, because you can see the paper came out in 24. He ran the simulations in 2020, and I really wish we'd been able to make a proper prediction, but well, we probably wouldn't have made a big deal of it. But it's an idea, and it unifies a lot of things that a lot of other theory groups are talking about right now, is that these dense star clusters can also then provide a sort of natal environment, and eventually those will sink to galaxy centers or form the sort of proto-bulge of more massive galaxies. So again, coming back to the conventional wisdom, do you require direct collapse? Not necessarily. If you have super-Eddington accretion, the seed masses really stop mattering to a large extent for light seeds. But also, you have this new problem that black holes really do require some kind of anchoring from dense substructures if you want to keep them from just free-floating in the ISM and never doing anything interesting. So now let's turn to, let's say we've gotten something that's a decent supermassive black hole and we want to grow it more. We want to ask more about the normal AGN and quasar life cycle. So let's turn to the supermassive black hole growth. There's a few pieces of conventional wisdom that we've thought a lot about that I think are increasingly looking incorrect from a lot of different approaches in modern work. One is that there's this old conventional wisdom that fueling the black hole, getting gas down from galaxy scales to the black hole, becomes very inefficient at less than of order a few parsecs, what we call the black hole radius of influence, where the black hole starts to dominate the potential and the potential becomes more Keplerian. And I'll come back to why that's been said in a minute. There's also a long-standing problem that if you try to fuel the black hole, certainly at super-Eddington rates, but even at a modest fraction of Eddington, that you'd have so much dense gas in the central regions that it would fragment catastrophically and turn into stars. And there's this long-standing problem of how do you possibly get the gas through at fast enough rates to feed a quasar, solar masses per year, without it all turning into stars on the way in. And then another piece of conventional wisdom that we usually make is that the accretion disk, at least over a certain range of scales, is something like the sort of Shakura-Senyaev classic alpha disk type models, and in particular that the magnetic fields are weak compared to, the magnetic pressure is weak compared to the thermal pressure. And again, none of these are assumptions that everyone in the field is making, but you'll still see these sort of as common baseline assumptions for a lot of modeling and a lot of discussion. So how do you get gas to a supermassive black hole is a problem I've been interested in since the start of my PhD. I think now I've worked on almost all of the scales involved. So there's a lot of scales involved, right? I've gone to conferences that have the title, "How do black holes get their gas?" And it depends wildly on who you're talking to what that answer is, because there's so many different scales involved. And sometimes you'll go to conferences where what this means is how do you get from here to here or something in the process, where you still have 8 orders of magnitude in scale to go before you get down to the black hole. Other times it'll be a conference where you're focusing on here to here or something, or here to the horizon. And I haven't even drawn the true horizon here, it's further down off the board. But the idea is that on very large scales, okay, you have cosmic web accreting onto galaxies. On large galactic scales, things like bars, spiral arms, galaxy mergers can torque gas into the center. There's a lot of work that we've done and others have now done showing that this problem at a few parsecs isn't really such a problem, because if you have, we know there are still stars at a few parsecs away from black holes. And just like at large radii in a galaxy, even when the potential starts to become Keplerian, the argument was always when the potential starts to become Keplerian, things like bars get shut down. Bar modes are suppressed in a Keplerian potential. And that's true. Bar modes are suppressed. But there's a whole host of m=1 modes that are not suppressed and propagate just fine through that radius. And if you have a mix of gas and stars, they can torque on each other and cause strong shocks, just like the way we talk about a bar or a spiral arm torquing the gas, causing it to shock and fall in along the spiral arm to fuel the galactic nucleus on galaxy scales. And it's just basically the same process. It's bars within bars, Schlossman and Begelman and others' suggestion going way back. It's just, stuff within stuff. You just have to, they made the wrong choice to say bars, because it's not bars all the way down. It's some other non-axisymmetric mode is all. That said, I think there is a big gap in scales here, where the smallest scales that these simulations tend to be sort of galaxy ISM scale simulations and make approximations on those scales that are not valid on small scales. Things like, for example, infinitely optically thin cooling and many other approximations are often made here. And then you get down to the scales with more traditional accretion disk simulations, which are often focused on sort of the very central regions around the black hole, maybe the central order 100 gravitational radii around the black hole, where you can make other approximations like neglecting self-gravity of the gas, neglecting star formation, neglecting atomic molecular dust thermo-chemistry and things like that. So we've been pushing on this for a while, trying to link these. What I just showed was a host of different, completely independent, idealized simulations of different scales. But because I said this is a coupled problem, ideally you want to follow a bunch of these scales simultaneously. So work initially led by Daniel Zangles-Alcazar, and follow-up work by Rachel Cochran and Jonathan Mercedes-Feliz, and a student at Caltech, Jayden Bardati, has started doing more work on the radiative transfer to make more comparisons with observations from these, began the project of trying to sort of follow a wider range of scales in this problem, beginning from our cosmological simulations and just refining the resolution with inflowing gas during, the idea is you run your typical resolution cosmological simulation first at standard resolution with standard prescriptions for large scales, and you identify some interesting times where, say, you've got a very strong inflow into the smallest resolved scale on your large scale simulation, and then you go back to just before that time, restart the simulation, but now with a refinement algorithm to follow the gas in to as small a scale as you can go. And these simulations showed that you could get strong inflows, some weak, some strong, some AGN that are more small accretion rates, 1/100th of a solar mass a year, some that were 5 or 10 solar masses a year, all the way down to about 0.1 parsecs, or a fraction of a parsec in this case. Now, why did we stop at 0.1 parsec resolution, or a half a parsec resolution? It actually wasn't because the simulations got too expensive to run, continuing to refine and follow the gas down. It was because these made those same large-scale physics approximations that just stopped making sense. They also didn't have things like magnetic fields in them, so you could see things that were unphysical starting to happen. We had a simple prescription for star formation, which was doing very weird things at sub-parsec scales. It was obvious that the approximations we were making for the physics were breaking down, so that's why we stopped it there. But now with these new hybrid forged in fire methods, we think that we at least have a reasonable way to treat things like, resolved star formation, where you believe individual stars are actually individual stars, and you follow the sites of individual genes collapse, as well as, following the MHD, following multi-band. We have a 5-band on-the-fly radiation hydrodynamics algorithm that's fully coupled to the thermochemistry. Did a lot of work uniting opacity tables for this whole dynamic range of densities and temperatures, building some pretty huge opacity table lookups and fitting functions and things like that. And I'm sure there's lots of imperfections in all of this, but at least, it's trying to put all this in one, and then basically repeat the experiment of keep zooming in. And that's what this movie is showing. We're following the gas density all the way down from these cosmological scales of megaparsecs into the true AGN accretion disk scales here. And you see this particular initial simulation zoomed down to about the final spatial resolution around the black hole. The final sync radius was maybe 10 to the minus 4 parsecs, which is a few hundred Schwarzschild radii in this case, about 300 Schwarzschild radii for the mass of this black hole. And you can see as here it's just showing how pretty this accretion disk looks on sort of 100th of a parsec or to 10th of a parsec scales. But as you zoom in, okay, we've got the cosmic web on large scales. We see the sort of galaxy here. This is a redshift 4.4 massive starburst system. This is really meant to be a quasar. We picked the thing that had the highest accretion rate onto the small scales we could resolve in the parent simulation of our entire simulation set. So we wanted a big honking quasar, and that's why we chose this. So it's got a huge starburst on large scales, and there's a giant molecular cloud complex of about 10 to the 8 solar masses that gets knocked by a bunch of mergers and clumpiness past the pre-existing about 1.5 times 10 to the 7 solar mass black hole, and gets tidally torn apart. That's what that big arm structure was. It was the tidal tail of that GMC getting torn off, and then it circularizes around the black hole. If you've seen simulations of a TDE, there's some scales of this where you could sort of squint and imagine it's like a giant TDE, because it's the molecular cloud getting disrupted at a few parsecs instead of a star getting disrupted at a few gravitational radii around the black hole. And that's what circularizes and forms this accretion disk. And this is just showing, that in a temperature map, just as it's a very pretty picture, and showing we also have followed this up, continuing to refine all the way down to sort of ISCO scales in this simulation. And we also partnered with Nick Kaz and the group at Northwestern. So the one limitation of these going down to these very small scales is that they don't have GR. We just use like a Pyczynski-Witte potential for the black hole. So we worked with Nick, who has, and the GRMHD code Hammer, best paper title I've ever worked on, a hammer forged in fire, to go down to the horizon and look at things like jet formation, where Nick basically used our inner region as his outer boundary conditions and initial conditions for his small scale simulation. And the thing that really jumped out that was really surprising from this, so we were expecting to just be able to show, the goal was to show that you could form an accretion disk. That was, where we were ready to declare victory. This is super exciting. The thing that we definitely didn't expect is the form and nature of that accretion disk that emerged. And in particular, what emerged is that these accretion disks, especially at the large scales, large for the accretion disk community, small for the galaxy community, the outer parts of the accretion disk, are really strongly magnetized in the sense that the plasma beta, the ratio of thermal to magnetic pressure, is extremely small. So a traditional sort of alpha disk model assumes something like that the magnetic pressure is 1 to 10% of the thermal pressure is a common assumption, or at least of the toroidal or tangled magnetic field component. You can have a stronger vertical field in principle. Whereas here we get that the magnetic pressure is stronger by a factor of 10,000, the thermal pressure in the outer parts of these disks. And I'll come back to what exactly that means in a bit. But we also found that the fields were predominantly toroidal, meaning they're wrapped up in the plane of the disk. Okay? And that's also quite different from what most accretion disk models assume. And again, it's not that nobody had ever seen or suggested anything like this, but this is certainly quite different from the sort of de facto model that is usually assumed. And this is just showing some of that quantitatively. I already said this, the sort of magnetic pressure the turbulence is sort of in equipartition with the magnetic field everywhere. In the inner regions, this thing is accreting at super Eddington rates. In the inner regions, the radiation pressure is comparable. So you sort of have, in the inner regions, you get radiation comparable, magnetic comparable, turbulent energy densities, with just thermal being much smaller than all of those. In the outer regions, of course, the radiation pressure is very small comparatively. So those are more purely magnetic and turbulence dominated. So I want to spend a few minutes and say just a very toy explanation of why does this happen? Why do you get this disk that's so magnetized in this way? And why didn't we see this in the sort of, why doesn't this happen in the sort of default model? So let me give the sort of conventional wisdom intuition. So you have some gas that's going to accrete around your black hole from the ISM, let's say. Now I'm going to look at that edge on. So here's a bunch of gas, and here's the black hole. What I usually assume, often implicitly on large scales, is that either that the magnetic pressure is weak, or that the magnetic fields are sort of pure vertical, lacing the disk. Again, these aren't the only assumptions, but they're definitely common assumptions for the large-scale magnetic strength and topology of the incoming flux of the magnetic flux, sorry. So, well, what happens if you have a vertically magnetized disk and you have gravity pulling it down towards the midplane? It's going to collapse, right? It's going to collapse along the field lines towards the midplane, and it's going to keep collapsing because magnetic fields won't stop this collapse until something like the thermal pressure builds up because it gets dense and optically thick enough that it's able to balance the gravitational force. And when you do that, you predict that you get a very thin disk. In the outer radii, Kursiniaev alpha disks, even gravitoturbulent disks typically predict h over r of something like 10 to the minus 3 to 10 to the minus 2. Razor thin. This is like a sheet of paper out here, the thickness of the aspect ratio of the accretion disk. And then once you've collapsed, you start to develop things like the magnetorotational instability that give you a turbulent magnetic field and velocity, and this gives you Reynolds and Maxwell stresses that allow you to transfer angular momentum and accrete through the disk. But importantly, if you've collapsed to this state, you will never build up the magnetic field, especially a coherent toroidal magnetic field, to the state that I was showing earlier. You've lost. The energetic cost of digging yourself out of this incredibly dense, thin disk is way too high. So if you start from this initial condition, you will never amplify B to see the other state that I was showing, which is part of the reason, not all, that it hasn't, I think, been studied as much in the literature. But this also can cause a lot of problems, and there's a lot of problems that we've known for a long time are associated with some of the standard accretion disk models, and there's a lot of work on understanding and reconciling these problems. Somebody like Julian here has worked a lot on the theory side of this, and I'll let Nadia and others tell me where I'm saying things terribly wrong about the observations, but one of the problems is at large radii, these disks are wildly gravitationally unstable, and we've known that for a long time. This is related to that argument that they would shatter and turn into stars rather than accrete. There's also, at small radii, you can get thermal and viscous instabilities that don't appear to be seen. There's also various issues reproducing the right disk sizes, and there's questions about the spectral shape, although that's a much more tricky question, and about reprocessing layers, which themselves, and variability, because you generally predict that the variability times, if it's accretion disk variability, are very long and very slow variability, and can't explain a lot of the variability we observe. And related to what I'm saying here with reprocessing, there's not the stuff we see. Like, this is the toy model I just drew. But of course, if you've ever read anything about AGN, this isn't the picture of an AGN. The picture of an AGN looks like, this isn't as pretty as most of them, but there's a bunch of stuff. There's drawings of clouds floating above the disk. That's your broadline region. You've got a big donut. That's your dusty torus. You've got, maybe they've hatched out some region, and maybe it's the base of the jet. Maybe it's a sandwich corona, but there's some coronal gas. You've got some layers that are doing things like Comptonizing the gas to explain things like the soft excess that we observe. There's a lot of layers that have to be sort of bolted on to this model that we know are there. And there's natural reasons for some of those layers to occur, but some of them have been challenging to explain certain properties of, from a physics point of view, why they would emerge for a long time. So for example, one challenge has been, what's keeping the broad-line clouds up here. And there's definitely more than one idea for that, but it's been a long-standing question. And I think it's fair to say it's certainly not a resolved question that we have a consensus on. So coming back to why this type of disk happens, the key difference is really that boundary conditions really matter. And we've known that from the idealized simulations of small scales as well, but we're just seeing that from this particular large-scale boundary condition. So the idea is, okay, gas is going to accrete from the galactic ISM into the black hole radius of influence. I said you've got this big cloud, and it gets sort of tidally torn off and starts to wind around the black hole and circularize. This cloud, just like most molecular cloud complexes, has a bunch of tangled velocity and magnetic fields in it. It doesn't have a lot of super coherent magnetic field inside the cloud. But when you rip off a chunk and start stretching it, that tangled B field gets stretched into a preferentially toroidal field configuration, basically. In fact, you preferentially suppress any net Z component if you take a loop or a tangled blob of field and start tidally shearing it out in this way. You end up transforming it into a more toroidal field that's stretched in this configuration. And that's, again, this is the toy geometry, but that's very much what we see. These are just some images of this filament wrapping around. These points are all the stars that are forming in this, or that were in it from the pre-existing GMC as it got ripped out, basically. And here's just showing how the field gets wound up. You can see it's a little more disordered on large scales, and it gets kind of more and more ordered here. And in fact, these blue and red are sign flips of the sign of the toroidal field, and that's because this was a random turbulent field that you stretched out. So every so often you switch signs from the large scale field, which, as a complete aside, by the way, if you want like interesting sites of star formation in AGN disk, these are the sites where the field configuration is switching, are sort of the ideal places where you could collapse a little bit of gas and form stars in the disk. And things like this have been seen in a number of simulations. The first that I'm aware of, although there might have been others, was Yevgeny Gabarov and Yuri Levin saw something like this in a GMC with a turbulent magnetic field being disrupted in an analytic potential toy model that they ran in 2012. And then more recently, there's been multiple efforts to do this kind of hierarchical zoom-in. I mentioned the work by Yanlong Shi, Minghao Guo at Princeton, and now Haiying Wang working with Elias Most at Caltech have seen this. And it's worth noting, also there was a similar result by Luo and Schlossman last year. It's worth noting that these also now have been seen in at least 5 different codes with 5 different treatments of things like the ISM physics and the different details. So it helps somewhat reassure. There's definitely numerical questions I don't have time to go into about convergence and things like that from these kinds of global simulations. But it's at least somewhat reassuring that this is qualitatively being seen in a lot of these different environments. So you end up with this toroidally wrapped magnetic field. Very briefly, what happens now if my gas tries to collapse vertically as it cools down and gets pulled down by gravity? Well, that toroidal field resists the gas vertically collapsing. So if you're familiar with magnetically arrested or mad disks, those arrest the gas sort of coming in radially. This is more like as you form the disk, you arrest it vertically from collapsing into that thin state. So you actually end up with this quite puffy disk out here that never gets to that super dense state. So it's really, bimodal. You won't get into that state at all here, whereas if you got into that state, it's very difficult to get back to this state without some new accretion. And so actually, ironically, even though this has beta much less than 1, because you stop the collapse and this disk has so much lower density, so the thermal pressure is so much smaller throughout this disk because it's so puffy compared to that super dense disk. B is actually slightly smaller in this big puffy disk than in the Shakura-Sunyaev disk. The actual value of B is bigger in the Shakura-Sunyaev disk, basically. It's just that here it held it up before you got to those extreme densities, basically. Okay. So you also get very strong Maxwell and Reynolds stresses from this that start to drive very efficient accretion, and you can accrete very, very rapidly. So the accretion time can be, multiples of just a few of the orbital time, for example, in these cases. So, why do you care if you like accretion disks or care about AGN at all? this really changes a lot of the accretion disk properties. So, here's an example. I take the same simulation. This is the simulation on the right that I just showed. If I just remove the magnetic fields, this is what I get. It just collapses vertically, and that's basically collapsing down to the resolution limit. The disk is basically one cell thin at this point, is all I can get to. So it really changes the geometry of the disk, which will completely change things like the reprocessing of radiation as that's coming out, as well as the variability timescales. The gravitational stability is completely different. And we see this in a lot of manifestations. So here's, for the same left and right simulations, the inflow, outflow, and star formation rates. So if we turn off the magnetic fields, our inflow rate in the inner accretion disk drops by like a factor of 1,000. Our star formation rate grows by a factor of 100,000. What's happening is exactly what was predicted, that the disk is shattering and all the gas is getting eaten by stars, and they're just not able to get much gas through to the black hole. There's a lot of other interesting predictions. You get a lot of multi-phase turbulent structure in these disks. They cool differently in their outer regions. This is just an excuse to show a pretty movie because it's been too long since I showed a movie. Same zooming in, but just showing the where sort of thermal pressure versus turbulent pressure versus magnetic pressure is most important as we go from sort of galactic scales to the galactic nucleus, where they're more in equipartition, down into the accretion disk, where you'll eventually see the accretion disk becomes sort of completely red-yellow as the magnetic pressure gets more important. Again, I mentioned reprocessing. Jaden Bardati is a student working on some first radiative transfer calculations to look at how this would actually affect observables about AGN disks and whether that can actually address any of those problems I brought up. I think hand-wavily it might help with some of those problems. There's good reasons to think it will, but we need to ask this quantitatively. Also with Dalia Baron and Asha Piotrowska, we're looking at, for the very outer disk, we have strong constraints on disk kinematics from maser constraints. Where we often see very close to Keplerian rotation curves. And you can show that this translates into a very strong constraint on what dominates the pressure in the accretion disk. And I'm happy to talk more in detail about this, but the idea is basically if you have this sort of thermal pressure dominated disk, because you end up with the accretion timescale being very long, to supply the same m dot, you need a much more massive disk. And that predicts deviations from Keplerian rotation curves that are significant at maser radii. So you end up with a very strong constraint from a combination of gravity, masers, and some ALMA at larger radii that seem to strongly favor these magnetically dominated models, certainly over pure thermal pressure dominated or radiation pressure dominated. Now this is quite large radii. This is 10 to the minus 2 parsecs and up. So most accretion disk people probably wouldn't believe if you told them extrapolate your accretion disk to 0.01 parsecs. So yeah. This is a straw man that we're a bit arguing against, but at least there's some evidence that at the very largest radii where the disk forms, you have to have some strong other form of pressure there. So to summarize, the fueling from galaxy scales is actually quite efficient at these intermediate radii. Super Eddington fueling can definitely happen. It's not a huge problem at these radii. How super Eddington is an interesting question. But that can be fine because of these kinds of magnetic structures in the disk, and this really represents a sort of new area of parameter space for us as theorists to play with, where again there's been a little bit but very little work. So in the last 2 minutes, I'm just going to tease some stuff about feedback that we've been doing, because I don't have time and I could give a whole talk about feedback on its own. There's a lot of conventional wisdom, including some that I'm probably responsible for loudly promoting, like that we can get away with some effective efficiency that's order of % of L going into quasar winds or something, and that solves everything. I definitely said that at some point. There's also an old conventional wisdom. This one I'll blame on Darren Croton, writing papers at the same time, that if you have a hot halo in the circumgalactic medium, that means you have effective AGN feedback, and that explains why the break in the stellar luminosity function is where it is, because AGN feedback gets efficient at this magic halo mass of 10 to the 12.5 or something. And there's also a conventional wisdom often in the CGM, and especially cluster and group community, but even in the CGM and the Milky Way, that the non-thermal pressures are small, or at most an order 1 correction to the thermal pressures. And I think all of these are wrong, is the point. We know we need feedback. All I'll mention from Forged in Fire is we zoomed in, but of course, we haven't done the full coupled problem back out. So we're doing that now. That's a lot harder. This is the first time in my life I've done simulations where it took more than 1 second of real physical human time to advance the simulation 1 second of time in the simulation world. So you can't run this for 1 billion years. I can't, at least. And so what we're doing is various tricks to try to zoom back out using the small scale simulations as an effective subgrid model to build back out. And there's a lot of interesting numerical and open physical questions about how to do that, but we are sort of being able to follow these jets out. They're back out to about a parsec right now. So we're getting to interesting places of them interacting with the ISM. Again, other students have looked at things like the radiation. Jonathan Mercedes Feliz has looked at the winds and is looking at different types of models for those. Nadine Solomon at the radiation-driven outflows, especially from the torus, and Sam Panada at cosmic rays accelerated either in the base of in the jet acceleration region or further out in jet termination shocks. Sarah Wellens and Lindsay Byrne have been looking at, can this give on large scales, parameterized in some simple subgrid model, a good quenching? And basically what they're finding is a problem lots of people find, that the models that work really well on large scales fail. If you try to make a model that quenches your very massive halos well, it'll tend to overquench your low mass galaxies and vice versa, if you assume there's just a universal efficiency of feedback everywhere. And we were hoping to see if this Toy Story was true that Darren convinced me of at one point, that the hot halos are the key to AGN jets coupling. We would have been able to see that in these simulations. Those are well resolved, and that doesn't happen, basically. There's no magic transition there. There are, however, interesting hints from these small-scale simulations about an old idea, again, but one I think is really worth looking at now with these intermediate-scale simulations, that the difference between having strong jets and weak jets might be related to the state of the gas in the ISM on intermediate scales between the accretion disk and the CGM, where basically that Forged in Fire run with that dense starburst and high accretion rate, that jet gets launched but then dies within a couple hundred gravitational radii. It slams into way too much column of gas. It's never going to propagate out all the way to infinity with a lot of power. And it turns into sort of hot bubbles that leak out. When I say it's gotten to a parsec, it's more like the winds and parts of the shocked stuff have gotten out that far, but it's not, it's definitely not going to be an FR2 or something like that ever. So the other thing we're trying to look at is the effect of cosmic rays as a feedback agent on these large scales. And a lot of students, Isabel Sands and Margot Fitzaxon, have been looking at different diagnostics like gamma rays and high energy diagnostics. And in particular, Isabel, Sam Panada, and a student, Emily Silich, have been looking at, are there telltale signatures of cosmic ray pressure in the circumgalactic medium of both L-star galaxies and more massive ellipticals, large groups and clusters, that we can use to both understand cosmic ray physics better, as well as to understand AGN feedback channels better. And that's the teaser for, I'll talk about this in my discussion. This is from papers that I was going to talk about in the archive discussion tomorrow, for those of you who are able to make it. So this is just a teaser. If you want to hear about that, the argument I think that we're making is that there might be actually a lot of evidence for cosmic ray pressure dominated circumgalactic media already. They could already be there, and we just haven't recognized it in the existing data. So thanks very much.
All right, I think we have time for some questions.
Beautiful talk, Phil. Thanks. So your last couple slides leads right into my question.
Yeah.
Is, are you guys finding these sort of very broad and general properties of these winds and jets that are launched from black holes with these hypermagnetized disks compared to traditional disks, like in general more massive or faster?
So I think one thing, a lot of this is going to be, take it with a grain of salt, because this is super preliminary and we've just started analyzing a lot of this. The things like some of the fast winds that look kind of like, BAL winds or something like that, have a much broader opening angle in these simulations than you get if you have because basically the disk is thick and flared. you have a big working surface to launch these winds off of. Whereas if you look at some of the more idealized simulations, folks like Daniel Proga have done beautiful idealized simulations of the launching of those winds with I'd say, better treatment of some of the radiative acceleration physics. But they had to sort of introduce some hacks to get the disk thick enough, basically. Like they sort of force the disk to be thicker to have a working surface to work off of. If you just let it collapse here in the run without magnetic fields, you basically generate very little wind, even if you force more gas into small radii. You also just lose a lot of the accretion rate. So that's one immediate difference. Other ones, it's a great question. I don't know. We're really trying to think what are the sort of unique diagnostics of this. We're also trying to understand how it links to, there's a lot more work on these MAD disks where you might have a more dominant poloidal field in the central regions. And Nick in particular saw sort of transition in the simulation from this sort of toroidal to poloidal as you go in there. And there might be some signatures of that transition. That could also show up in some interesting variability signatures like flares, because you can get things like, because you're kind of accreting turbulent magnetic flux, you can occasionally get sort of polarity switches in the jet and the central regions. So again, I'm speculating a lot, but yeah.
Okay, so Julian Crowley.
Okay, I'd like to go to the question of how you get super low beta.
Yeah.
I want to begin by saying that every global accretion disk simulation ever always gets a magnetic field that's dominated by the toroidal component, because as soon as you have radial field and orbital shear, you've got B5. Okay. So really the question is, in terms of your simulations, the essentially correlation length of BR. Because if you have a lot of radial field here in this direction, and next door radial field in the opposite direction, it'll just cancel when sheared into toroidal field. So how much does the very low beta you get depend on some coherence in the initial magnetic field at large scales?
I think it depends a lot for the same reason that you just said, and we made some back of the envelope estimate of this in terms of effectively, another way of saying what you're saying is sort of the competition between the amplification you get from shear versus the turbulent resistivity that you would get, or whatever you want to however you want to parameterize it, the cancellation you would get basically. And so in these, because you have this very stretched field from large scales, you get a very long coherence length of BR in the outer disk. And so I think that plays a key role.
So you're picking out just one small region to stretch.
That's the thing. So I think exactly. So my intuition is that there would in this case, the parent cloud complex that got tidally disrupted to form this disk is actually much larger spatially than the radius of influence of the black hole. It was like a 100+ parsec size cloud complex that, versus a few parsecs radius of influence. So it's a small fraction of the coherence length of the parent cloud complex that got pulled off. Whereas the regime you're talking about might well happen if I imagine a cloud that's smaller than the black hole radius of influence. If I have a cloud that's like half a parsec accreting into the black hole, then the coherence length would be small compared to that scale. And
you imagine that the largest cloud is filled with turbulence, and turbulence spans many length scales.
Yeah, well, it is turbulent. It's just that, it gets, when we look at it, the usual result that we get the usual result that most of the power is on the largest scales. So the effective coherence length is dominated by the driving scale.
When you're referring to beta, is the field being compared to just the gas pressure or gas plus radiation pressure?
Yes, so in the inner region, gas plus radiation is much more like beta of 1, which is completely consistent with the inside-out simulations of strong super Eddington disks. So there, I don't think there's actually any big tension. Well, I think in the outer disk, it is a real 10 to the minus 4, even when you include the radiation. And I think that's where, but there you also have to be careful that part of the reason that beta gets so low, and that some simulations haven't seen it that low, is because since this has things like atomic and molecular thermochemistry, the gas can get very cold, right? The outer disk can have molecular gas, where beta is super low because, the sound speed is 0.1 kilometers a second, right? And that happens in molecular clouds too. So I agree, it's not as extreme as it sounds at first, and I think that's an important point. Yes. Thank you for calling it out.
Time for one more very quick question before Estes.
Okay. Quick, I don't know. I'm looking at this movie over and over again, and I'm trying to figure out which physics is included here.
Yeah.
And so, first of all, there doesn't seem to be a torus, so it doesn't seem like the radiative transfer and the infrared is included.
So there is, this is including the radiative transfer, and there is a torus. There's sort of a gap. It's also a bit an artifact of the choice of density scale that I'm rescaling this with. So the student, Jaden, that I mentioned, his first paper, which should come out in a couple weeks, is looking at the IR radiative transfer. I actually told him to send a copy to you specifically, but looking at, the effective torus is this arm of the molecular cloud that's been torn off, and it has a vaguely torus-like morphology. And, the inner boundary is just the sublimation radius like you'd expect.
Aspect ratio. Do you get a reasonable aspect ratio?
He does. The main thing is, though, because this has, such a high Eddington ratio, and probably also because we haven't evolved the feedback going all the way back out, while the disk aspect ratio is quite reasonable for a torus, the polar region, it's definitely much less dense in the polar region than in the planar region, but it's still enough that it's optically thick in the optical UV. So it's a more isotropically obscured AGN at this stage.
One super quick.
Yeah.
It's grainy at like 10 parsecs.
Yes.
Zoom out.
Yes, there's a little stage where it's grainy. That's mostly a visualization artifact of how I made the movie. It's also a little bit, it's how the visualization played with the refinement algorithm. There's a little bit of an artifact of the refinement algorithm there, yeah. But not real. I wish it was, because yeah.
Okay, so I think we're basically out of time. There is an SDAS today. It's going to be outside past that cafe, so please join if you have more questions for Phil. Thank Phil again.
Is that